Hello friends, welcome back my YouTube channel MS Maths. In this video we are going to discuss the theorems of measurable sets. In the previous lecture we have discussed that what is the measurable set. If you have a set E, basically it is a measurable set. It means that the outer measure of any set A is nothing but the outer measure of A intersection E and plus the outer measure of A intersection E complement. So this property we have discussed, and there are some 2 to 3 properties or 2 to 3 relations of this the terms that we have already discussed in our previous videos. In this video we will discuss 3 to 4 theorems related to this particular result. So we will prove all these theorems. Then let's take one by one. So first theorem we have that a set whose outer measure is 0 is a measurable set. Like it is the statement, or we can say that if E is a measurable set, or like basically if the outer measure of E is 0, then E is a measurable set. That we have to prove. Now we are going to prove this. So proof. So basically let A be any set of real numbers, then outer measure is basically M star A, that is the property is less than equals to M star A intersection E plus M star A intersection E complement. Okay, so in this way we have this equation number 1, and we'll put also A intersection E is subset of E. Okay, A intersection E is subset of E, and A intersection E complement is subset of A. Obviously, because the like intersection with the complement is nothing but A. When this, it implies that the outer measure of A intersection E is less than equals to the outer measure of E, and the outer measure of A intersection E complement is less than equals to the outer measure of A. Okay, by using this, like taking the outer measure in these both condition. Now adding all the terms, adding these two terms, we get the result or the definition of the measurable set, or Lebesgue measurable. That is basically the outer measure of A intersection E plus the outer measure of A intersection E complement is less than outer measure of E plus outer measure of A. Given the outer measure of E is equals to 0, it means the outer measure of A intersection E plus the outer measure of A intersection E complement is equals to the outer measure of A. This this is the condition, or basically, yeah, in this case that is not equal, that is less than equal. Okay, that is less than equal, and we have already considered this is like outer measure of A is less than this, like this is the property we have, and here it is greater than. Then by using equation number 1 and 2, we will take this is equation number, this is your equation 1 and this is equation number 2. Then by equation 1 and equation 2, it is nothing but M star A, the outer measure of A is nothing but outer measure of A intersection E plus outer measure of A intersection E complement, sorry, it is E complement. Then E is a measurable set by the definition of measurability. Now next theorem we have, if outer measure of E is equals to 0 and O be the set of E, then O is also measurable. Then okay, now let's take it as some, I say S. Instead of taking O, I will take S. Okay, so basically if the theorem is S is also measurable, since S is subset of E and E is measurable and given condition is the outer measure of E is basically 0, then it is a subset of E, then outer measure of S is less than equals to the outer measure of E. Outer measure of E. And outer measure of E is basically 0. Then it is nothing but outer measure of S is equals to 0. It means that it is also satisfy this condition. Then it implies S is a measurable set. Very simple. Next theorem we have, if E1 and E2 are measurable set, then E1 union E2 is also measurable, or basically the union of two measurable set is measurable. This is very important property that we will prove. Now, what is the proof? Let A be any set of real number, then outer measure A is equals to the outer measure of with E1, intersection with E1, plus the outer measure of A1, A intersection E1 complement. That is the simple property of the measurable set. Then outer measure of A intersection E1 plus outer measure of A intersection E1 complement intersection E2. Okay. Now that's we have written in this way. After writing the like term, that you will get why we will write it as since E2 is measurable. Okay, E2 is measurable, then we can write in this way that if E1 and E2 union, we want to find the union, then outer measure of this complement we can write in this way, that intersect with this and intersection with this. Here E1 is not complement, here E1 is not complement. Okay, then it implies that the outer measure of A is equals to the outer measure of A intersection E1 plus the outer measure of A intersection E1 complement intersection E2 plus the outer measure of A intersection E1. We will take together these two things, or basically wait intersection, then if we take the complement of these both, then it will be union of E2 and it will be the complement. So here is also complement, and this will be union. Okay, now A intersection E1 union E2 is nothing but A intersection E1 union A intersection E2 by De Morgan's law. Then we can write it as A intersection E1 union A intersection E2 union E1 complement. Now, taking it is all with the like simple outer measure, then taking outer measure. So outer measure of A intersection E1 in a union. Okay, outer measure of A intersection E1 union E2 It's less than, obviously, because this is union of these two. Then it is less than outer measure of A union E1 plus outer measure of A intersection E2 intersection E1 complement. Then by using countable subadditivity, what it says, using this is basically the countable sub using additivity. Then using 2 in equation number 1, we get, I say this is 2 and this is equation number 1. This we will use in this case. Here we have the value of this complement. I think this value will use. So we get the outer measure of A is greater than the outer measure of A intersection E1 union E2 plus outer measure of A intersection E1 union E2 complement as it is. So basically it is necessary and sufficient, the necessary and sufficient condition for sets E1 union E2 to be a measurable set. Okay, this we have already proved. So and E1 union E2 is measurable. Okay, so this is the condition that we had already. Basically what this represents, the outer measure of A is equals basically the outer measure of some A intersection with E plus outer measure of A intersection with E complement. This is the representation for this, and according to this condition that we have already discussed, it is the necessary and sufficient condition, then we can say that it is the basically it is the measurable set. Now prove that the intersection and difference of two measurable sets are measurable. Now we have proved the union. Okay, now we'll proceed forward with the intersection and the difference. Okay, then proof. Let E1 and E2 are two measurable set. Then we have to prove the E1 intersection E2 and E1 minus E2 both are measurable. That's what we have to prove. So first of all, by measurable, that E1 intersection E2 complement is nothing but E1 complement union E2 complement, by the definition, by the property. Since E1 and E2 are, since E1 and E2 are measurable, therefore E1 complement and E2 complement also measurable. That is the property of the measurable set that we have already discussed in our previous lecture. And also in the previous theorem we have proved union of two measurable set is also a measurable set. Then E1 intersection E2 complement is measurable. Because of that, it is nothing but E1 complement union E2 complement. Now see, this is the measurable set, this is the measurable set, then the union of two measurable set is again a measurable set. So that's why it is a measurable set. Okay. Then we have wait, okay, the complement of complement E1 union E2, okay, or basically wait, then E1 intersection E2 complement of complement is nothing but E1 intersection E2 is also measurable. It is measurable set and it is the complement of measurable set which is also measurable set. Now our aim is to prove the difference E1 minus E2 is nothing but E1 intersection E2 complement. Now we have E1 and E2 are both measurable set, then intersection of and E2 complement is also measurable. We know that the intersection, that's we have proved already, intersection of two measurable set is measurable. Then E1 minus E2 is measurable. So these are the theorems that we have proved, and these are the different type of theorem but based on some like the same concept. So this is all about the theorems. So thanks for watching my video. Keep watching MH Maths, and for these types of videos and for higher mathematics you can follow my channel, subscribe the channel so that you can get the notification first. Thank you. Bye bye.